You know, it's interesting to be up here, and thank you very much, Tim, for inviting me today. It's an honor to be here. This is the second time I presented at an antenna forum at the Dayton Hamvention, now the EZNEC Hamvention, and the last time was 50 years ago. Thank you. So a little story, it's how I learned about SWR. Started when I was taking my novice courses and took some of the, took an excursion to a ham who was a contester in the RTTY business. This was in 1964. And I think I'm going to turn this up just a little bit if I can. There we go. So the guy who's teaching me the theory basically says, okay, when you have an impedance bump in a transmission line, some of the signal gets transmitted back to the transmitter. And oh, by the way, it excites the output circuit, and that turns it back down and goes up to the antenna anyway, but a little bit more of it is lost, in other words. I said, okay, that makes sense. And then we went to the field trip to the guy that made his own kilowatts, and he was a broadcast engineer, and he says, don't ever use a barrel in your RG8, because if you do, all the signal that is reflected back is totally lost. So I said to myself, okay, this is interesting. I have a guy whose theory makes sense, and I have a guy who's got experience, and the two of them don't agree. So this is going to be interesting. So I thought of it myself, and I said, okay, which one is right? Well, obviously, the guy that said it in theory is correct, and the guy who's experienced didn't actually make any measurements. He just thought it was the case. And later on, I had some other experiences about SWR. My first job out of RPI was I worked for Sylvania, and Sylvania was building radios that went into the helicopters, and they had a problem with their UHF module, because the UHF module suffered transistor failures in high SWR. So, why is that? And I was helping to work on the test procedures for it. I wasn't a design engineer. The design engineer was Gil Bolke, W2EUP, who's been dead for years now. But many of you people, anybody that's been familiar with 2-meter FM knows that he was the guy that built the first frequency synthesizer. And these radios were fantastic. They were the size of the Collins control panel, and it was the entire radio. And the solid state, 220 to 400 megahertz, 10 watts of AM. It had 5 transistors in parallel. The collectors were actually connected together in a pentagon. The problem is that when the people in Vietnam would hose off all of the crud from their helicopters, they would cause water to get in the antenna. The SWR would go up, and the instantaneous voltage on the collectors would go so high that the transistors would fail. Does that sound familiar to what's happening today in the ham radio world with solid-state amplifiers? It's exactly the same thing that's happening. So there's something I was working on then, and the solution back then was the same as the solution now. Put a hot carrier diode on the collectors, measure the instantaneous voltage, and if it goes to anything higher than twice the collector voltage, your transistor will fail, and you must eliminate the drive to that as quickly as you possibly can. My next experience with SWR is that when I got into the TV business, I was primarily a studio person, and at one point, my boss, who was taking care of the transmitter, says, we have a nitrogen leak on the antenna. I'm going to get the antenna crew to come in, and I'm going to have them fix the nitrogen leak. Okay, no problem. I want you to come up there. Oh, okay, I can do that. So the guy fixed the nitrogen leak, and he put the antenna back together and turned the power back on in the TV transmitter, and the SWR was 1.3 to 1. And the TV didn't like that. Why not? Because that signal comes down back into the transmitter. And just like I learned from my guy in the novice, the signal goes back up to the antenna. There's only one thing wrong. In a TV, time matters. And there was a transmitted ghost because the signal that was transmitted back to the antenna arrived later. And the tower climbing, the rigger that did the repair says, I put it together exactly the way I took it apart. It's not my problem. He's going to leave. And of course, my boss knows that this isn't right. It's time to fix it. So the rigger says, I'm leaving. So he takes his rigging off the tower, and he drops his 40-pound block that he's got his cable on, and he dents the feed line. And he happens to dent the feed line in exactly the right spot at exactly the right amount to cause the SWR to go down to 1.05 to 1. And he said, no, the problem wasn't there. Problem wasn't on the antenna. Problem was down here. Of course, if you look at the picture monitor, there's still ghost there. But the ghost, which used to be about an inch to the right, is now 7/8 of an inch to the right, because now that reflection is going back from the dent, not from the output of the transmitter. So all of a sudden, SWR is an interesting thing that you have to deal with. TV signals always want to see a 1.4 to 1 SWR or lower if you can. So with all of this information in the background, let's look just a little bit at how to match a dipole. I had my graph up there before. Everybody knows that graph. You've probably seen it in the handbook when you were 12 years old, didn't know what it meant. But it basically means that if your antenna height changes the impedance of your antenna. And if it's very close to the ground, it's 50 ohms, mostly because all of it goes into the ground. It's ground losses. The whole concept of an NVIS antenna, it has great SWR, but it has a lousy radiation pattern. And what you want to do is you want to get your antenna up to the point where there is no ground losses, and that occurs at roughly 1/3 of a wavelength. But 1/3 of a wavelength is only like 23 feet on 40 meters, and most people know that 23 feet is too low to the ground to be effective on 40 meters. So you have to put it higher. But as soon as you put it higher than that, it's no longer a 50 ohm antenna. And a lot of people say, well, just cut it to as close as you can and use it like that. Well, that's what everybody did for the last, 20 years or so. But you don't have to do that anymore. You can match that very easily by off-center feeding the antenna. So instead of feeding the antenna at the center point, which is maybe at that point maybe 60 or 70 ohms, what you do is you feed it maybe only at around 35% off, but now the impedance isn't 50 anymore, it's about closer to 100. So what you do is you say, I can transform 100 ohms back to 50 ohms using 75 ohm coax. And everybody knows that a quarter wavelength of coax transforms from 50 ohms to 100 ohms. Well, it doesn't really. It transforms from 112 to 50 because we're doing it backwards. About 112.5, but you can use EZNEC to tell you exactly where to connect that antenna. And this is something I've done effectively for field day antennas. And a lot of people told me, well, as soon as you off-center feed a dipole like that, you're going to need a big balun because you're going to have an offset pattern, and the pattern's going to screw up. Well, I put it in EZNEC, and the pattern is off by maybe 1/10 to 2/10 of a dB in terms of how much rejection you get. And I built this antenna, a coax, used that in field day, fed it with RG6, nice cheap coax, good low loss stuff, nice and light. And it should have a balun on it. I did it without a balun. Doesn't cause any problems without a balun. Works very well, made a lot of contacts. And if you do want to use a balun, I want to encourage you to use a Guanella balun. And I want to start off by saying this, is that there's a lot of controversy in baluns, and I'm going to tell you what my opinion is that a lot of people call them chokes. A choke implies that it's an inductance, and it could be, but it's better if it's not. A Guanella balun is specifically designed to equalize the currents in a balanced line. So you run the balanced line around the toroid, and if there's more current in one than the other, it creates a magnetic field in the toroid that then enhances the signal in the other one to equal the one that was stronger to start with. So it becomes inherently balanced. Or you can think of it as a transformer where it's pushing current from the stronger signal into the weaker side until they're exactly the same. And that is how a Guanella balun works. And that's the difference between a current balun and a voltage balun. And it's interesting because there are people who make these things and they think they're making a Guanella balun, but sometimes they're not. So as soon as you take coax and you wrap it around a toroid, have you made a balun? Absolutely not. You've made an inductor because the field from the center conductor is never ever seen by the toroid. So then if that's what you want to do, that's fine and dandy. W1JR, Joe Reiser tells you how to fix that. You wind the coax one direction for some turns, and then you wind it the opposite some more. Now all of a sudden the current on the outside is nulling itself, and the current on the inside just keeps going as if there's no toroid in the circuit. So when it's time to start working on this antenna and you want to know exactly where to use it, don't just automatically assume that you want to put it at the 112 ohm point and assume that it's going to work. You can actually model it. And what you do is you use the transmission line formulas in EZNEC to do the hyperbolic trigonometry functions for you. Anybody remember those formulas? You know, I learned them in high school, said, what am I going to use with these things? And well, all of a sudden I'm in transmission line theory, and there they are. And it's a lot of people try to make it easy by using Smith charts. That just, to me, it just makes it harder. And I got to understand two things that don't make any sense. But I'm just joking. I have done the math once or twice and said, well, with EZNEC, I don't have to. The way I do it in EZNEC is I will, put my dipole up, and then enter another dipole, maybe a foot off the ground, one segment long, as short as it will let me put it for the diameter wire that I have. And then I set the input of a transmission line to be the feed point of the antenna, have the transmission line end in this short piece of coax that I put, not coax, I mean the short line near the base of the tower, and then connect the feed point to that short piece, let it calculate it, and it tells me exactly what comes out. And if it doesn't end up with exactly what I want, then I can move the feed point one way or another until it works perfectly. And I do that for field day antennas, and it works real well. So we're going to start with looking at a 40-meter antenna because you can understand some of the concepts looking at a 40-meter antenna, and then we're going to transfer some of that knowledge to 80 because 80 is the real challenge that we need to deal with. So this is where our starting point is, a 40-meter dipole, 23 feet. You match it at the center of the band, and it's less than 2 to 1 across the band. And, do you want to operate at 2 to 1? Well, I find that if I have an amplifier that doesn't have a tuner in it that follows my frequency, or if I want to switch between antennas, I want it as close to 1 to 1 as I possibly can. So, and I'm often making this kind of an antenna for field day, and the people in field day don't know how to tune the antenna on rigs that you haven't normally used. And if you tune it up for the sideband portion, it's wrong for CW and vice versa. So this is not an adequate solution to me, but it does tell you what our starting point is. And this is what it looks like if you offset feed it. All of a sudden, what have I got? I've got 1.3 to 1 at the bottom of the CW band, 1.5 to 1 at the top of the band. Is it because I offset fed it? No, it just happens to have a better SWR curve when it's higher off the ground. Now let's take this a step farther. The bandwidth of a dipole is limited by the diameter of the wire used. And if you go back years and years and years and years in the handbook, they talk about cage antennas. They show these wires and big spreaders. I'm a TV guy. What do they do for UHF TV receive antennas? They use a bow tie. Well, if you analyze a bow tie in EZNEC, you'll find out that if you make a bow tie and you make every single whisker of a bow tie exactly the same length and you spread them a certain distance apart, you can get a nice little pattern. And the EZNEC says the best distance between the two wires of a 40-meter bow tie is 5 feet. Those wires end up being shorter by about 5 feet, roughly. And the following design, I used it at HQ9X last year in CQ Worldwide Phone. And again, here we're dealing with an antenna which is 1.3 to 1 all the way up to about 7.29. It's a really nice way to get a low SWR in 40 meters relatively simply. And everybody says a delta loop is a nice broadband antenna. Well, it's about the same as the bow tie. And if you happen to want a slightly lower angle, nothing wrong with a delta loop, but it's not a magic antenna when it comes to SWR improvement. Now, there's another thing that happens when you stack antennas is that the SWR curve gets better as you start putting antennas together. So this is basically two separate dipoles from one supporting tower. They're about 60 foot high in the center, and they're slightly fed off center, and it's got some matching transformers in it. But you get some gain, and this gain can be helpful, maybe only a dB to a dB and a half gain. And if you take this pattern, you say, okay, we call this in the TV business, they call that a peanut pattern. It kind of looks like a peanut. And you say, okay, I want that area where no power is going, I want one of it to be, I want it to go into none of it, because I don't want to put any power in none of it. Put the other direction aimed at the Bermuda Triangle. I don't want to waste any power in the Bermuda Triangle. Now all of a sudden you're a dB and a half stronger than anybody else on the band who hasn't done this. So, and your SWR curve is now down to 1.2 to 1 across the band, just because two antennas added together always gets better. Now W7ZZ came up with an interesting way to feed an antenna. You know, WWII Yagis have a first director that's very, very close to the driven element, and it gives you a very, very nice SWR curve. The problem is that on 40 meters, and the impedance of the antenna is too high to start with, and you can't make it lower with an OWA wire, you can only make it higher. So you make it higher by you put your wire on there and you say, okay, now I can use that same 75 ohm transformer trick, but now I can feed the antenna in the center with 75 ohm coax, 3/4 of a wavelength, 1/4 of a wavelength, depending on how it is. And now all of a sudden you have this curve, which is 1.1 to 1 up to about 70. Very, very, very nice curve. Now I'm going to dig into a very interesting thing. The people that worked on radar in World War II knew how to make a broadband dipole. And they were not necessarily electrical engineers. They were physics majors. And they were using RF energy at microwave frequencies in order to run their cyclotrons and linear accelerators. Well, these mathematicians knew how to do things in math, and they knew the formulas for transmission lines. And they used that knowledge to say, okay, what if we took a half a wavelength of coax, it's a lower impedance than the antenna, and at the low end of the band, it's less than a half a wavelength long, and at the high end of the band, it's more than a half a wavelength long. And oh, by the way that the transmission line theory works, it counteracts the reactance of the antenna in the exact opposite way the antenna is. So when you put that half a wavelength of coax in there, it has to be a lower impedance than the antenna you're feeding. And then you have to bring it back up to 50 ohms. And this is what a dipole looks like if it's fed at the 37.5% point with a half a wavelength of 21.4 ohms. Why 21.4 ohms? Well, it happens to be one piece of RG8 and two pieces of RG6 put in parallel. Now you got to bring it back to 50 ohms with a quarter wavelength of 75 ohm coax. And in order to do this in EZNEC, you're using EZNEC to do all of the complicated calculations for you. You just now have to set it up with multiple points where you're connecting the coax together and multiple pieces of coax. And now you've got an SWR curve that is about 1.05 to 1 on every frequency on 40 meters that you're likely to operate. And it only reaches above 1.1 to 1 at the top end of the band. Now we're going to deal with the 80-meter problem. This is what an 80-meter dipole looks like on an SWR curve with it at the height where the feed impedance is 50 ohms. And you can see that it's 5 to 1 SWR. Totally unacceptable. So now we're going to use that same radar match concept. In this case, we're using we're doing a little bit of an off-center feed. We're using a 25 ohm coax, which is two 50s in parallel. And then we're going to match it up to 50 ohms using 1/4 wavelength of 75 ohms. And now all of a sudden, instead of having a deep notch in the middle, we have a slight rise in the middle, and we have our dips down on either side. And on the frequencies that you'd like to operate on, it's never higher than about 1.75 to 1. And this is something that I came up with a couple of weeks ago when I was trying to decide, okay, I need a field day antenna that'll work on both phone and CW, and I don't know whether I want to put up a phone or CW antenna. And I said, wait a minute, I can make it be both. So here's a phone and CW antenna for field day. And it's just using regular off-the-shelf coax without anything special. So I said, okay, how much better could we get? Well, I took the concept for W7ZZ design, put an adjacent wire next to it, and then I used the radar match and using just a half a wavelength of 50 ohm cable, you got to come down from the antenna anyway, and then the transformation, and all of a sudden now I've got an antenna which is less than 1.3 to 1 everywhere in between the phone and CW on 80 meters and 75 meters simultaneously. Would you actually build this? When I show this to people, they typically say to me, well, how do you keep them spread apart? So I don't know, I've never built it. But what I would do is that I would go to the hardware store and I would buy a piece of 1/2-inch PEX and cut it and make it like ladder line with 3-foot spacers. And you probably need one in the middle and one at each end and hang it, and voila, you can end up with something like this on field day, which would be very, very helpful in field day. So then I said, okay, let's try the same techniques on a vertical. And I'll be honest with you, Tim Duffy started with me on this concept. What can we do about improving the bandwidth of a vertical? Because what happens in a 4-square is that you can get losses in a 4-square if the SWR rises. Some people call it waste power, some people call it a reject power. That's what we call it in the TV business, is reject power. And in a perfectly balanced system, the reject power ends up in the dummy load. And if you're running a TV transmitter, that's actually a good thing because that's the reflection you want to get rid of. But it is still heat. But on 80 meters, your SWR is high enough where that can hurt your signal strength by maybe almost a dB if you're at the edges of the bands. So I says, what if I took a adjacent wire and put it next to a quarter-wave vertical? Oh, what do you know? It looks like that. And a quarter-wave vertical is typically in a mid-30 ohm feed point impedance. And in the process of putting in a wire next to it, it brings it up to a 50 ohm feed impedance. So you can have a tower that's the right height. You put a wire maybe 5-10 feet off to the side of it, so it's exactly the right length. And you don't need a matching section at the bottom anymore to match it from 30-some ohms to 50. It's made the whole antenna be exactly 50 ohms to start with. And then I said, okay, now let's try something else. Because putting a adjacent wire next to a 4-square would actually be rotating the 4-square slightly because the phase centers get off-center because of the spacing between them. So I said, what if we use this radar technique on a vertical? So this is what a vertical would look like if you set it to be 100 ohms at the end of a 75 ohm piece of cable. And in this particular case, instead of using one length of 10 ohm coax, I decided I would set it up as 2 different impedances that are roughly close to 10 ohms. Now 10 ohm coax doesn't exist, but you can synthesize that if you want, putting various pieces of coax in parallel. But the point is, when you feed a 4-square, they always say that the delay between the hybrid and the 4-square needs to be either 1/4 of a wavelength or 3/4 of a wavelength. And this matches that 3/4 wavelength possibility. So you can get much, much, much better SWR characteristics and much less reject power on a 4-square if this works. I say if this works because I actually haven't tried it yet. But the theory says that it will. And the theory also says that if you just put this in without anything else, the pattern of the antenna will rotate 180 degrees, which you can solve just by swapping your left and right coaxes back and forth, and now all of a sudden it's back to normal. But it should not change the pattern, and it should remove a significant amount of the dump power. And what I need to really test on this is what happens to the mutual coupling in this case, because I have not gone far enough to actually put a hybrid into EZNEC yet and try to model this with EZNEC with a hybrid. It's going to be an interesting process, but that's next on my list. So I can take my concept of using 2 wires next to each other and move it to an inverted L concept. Call it a double inverted L. Well, here's what it would look like. And I actually put this with radials underneath it so that I get a raised radial so I could see if that raised radials had any effect on it. And in this case, this is a 44-foot high inverted L, and instead of having 1 wire up and 1 wire off to one side, it's 2 wires up and a wire off in each direction, spaced apart. Could be hung up just like a dipole, and you need 1 spacer at the top and you can feed it at the bottom. This has a feed impedance of 50 ohms. Typically, people who make inverted Ls have a feed impedance of 25 ohm, and they need a transformer in order to match it. This needs no transformer. It's a 50 ohm antenna as it is modeled. So now it's time for winter field day, and the winter field day says, oh, if you operate 160, we'll give you extra points. Well, they didn't this year, but in the past they did. Gave you extra points for every band. And I was searching the internet for an interesting way to do that, and I came across this broadband wire antenna made by a guy named K5GP. And it's basically an offset fed antenna for 160 with a trap in it that makes it resonant on both 75 and 80 simultaneously. And I don't know how he came up with this concept. I got to give him a lot of credit for it. I haven't actually tried to understand all of the mathematics of this antenna, but I've successfully built it. It works extremely well. And it does have an SWR curve that looks like that. A very, very deep notch on 160 down to 1.1 to 1. At about, I set it for about 1850 because I figured I wanted to operate high in the band, because typically winter field day occurs on the same weekend as the CQ 160 contest. So so I figured that the best way for me to operate the CQ 160 contest was to be high in the band, away from all the people that were really down in the DX portion of the band. And this would give me the ability to work some people on 160. And last year in winter field day, I worked 19 people on 160 and gave them all contacts in the 160 contest. Well, they gave me contacts in some cases. Not everyone gave me the right report, but the ones that did, I counted those. But it was just kind of it's an interesting antenna design, and you can go to the K5GP website and you can find this how to make this antenna. And this is a 4-to-1 Granella balun. This works extremely well. This particular balun is not made with any of the cores that you normally use for baluns. These are cores designed by Fairlight for EMI suppression. So it's a fat coroid, and it's taller, and it's smaller in diameter. So what happens is that you have a greater cross-section area in these cores than you have in a standard FT240/43 core. This is 43 material. This happens to be 9 turns of wire on each side. And it's 2 1-to-1 baluns with the primaries in parallel and the secondaries in series. So this is a balun that is 100 ohms to 100 ohms. And the theory says that in order to get the best bandwidth on that, the impedance of the twin lead that you're essentially winding around that needs to have a characteristic impedance of about 100 ohms. Well, I didn't actually measure what it was, but I looked at it and it says, yeah, it's going to be close enough. It'll be a low frequency. And I put this together and I actually put a compensation capacitor in it. And this works extremely well on 160, 80, 40. I don't use it on 40. If I was going to use it on higher frequencies, I wouldn't use 9 turns. 9 turns is more than necessary. And this happens to be just silver-plated Teflon wire. This is number 20 gauge wire. And this works extremely well. How much power can this handle? Well, keep in mind, in a Granella balun, the amount of current or the amount of flux in the core that causes the heating depends on how mismatched your antenna is and how much field you're getting off the antenna. Well, we're intentionally offset feeding this antenna, so it's going to have some coupling into the feed line. So I don't know how much this is going to handle power-wise, but I will tell you that it will handle as much as 3 or 4 FT240 cores because of the characteristics of these cores. And these cores are actually cheaper than the typical FT240 because it uses less material and gets more cross-section area. So now we take the double L that I showed you for 80 meters, and we built it for 160, and this is what it looks like. Under 1.4 to 1, all the way up to about 1.94, and then it goes sky high. So you can't operate the top, 40, 50 kilohertz of the band, but this is a very easy antenna to put up. I forgot what height this is, but this is, no more than 90-foot high antenna. Now I'm going to couple of things together. And this is an interesting antenna that I just kind of dreamed up almost for just as an example of what you can do with EZNEC and antenna designs. In this particular case, it's an 80-meter antenna. It's got an adjacent wire to it, a la W7ZZ. It's fed with a quarter wavelength of 75 ohm cable, so it brings the impedance down to 50 just the way it's supposed to. And then off the center of that, I have a 40 meter antenna, which is brought down to 50 ohms by turning it into an inverted V. And it's made broadband because it's a bow tie. So that has a feed impedance of 50 ohms because you've decreased the impedance by bringing it into a V shape. And then the next thing you do is that because it's fed with a quarter wavelength of coax on 80 meters, now it's all of a sudden a half a wavelength of coax. And now it repeats the 50 ohms at the antenna to 50 ohms at the feed point. So now it's a transformer on 80 and just a regular impedance repeater on 40. Something you could put up permanently if you wanted to, something you could use on field day. And this is what the SWR curve of that looks like if you put it on a single graph where you can see the double tuned circuit for 80, 75 and a double notch on 40 as well. Now I'm going to talk about end-fed half waves. They're very popular these days. I've used them on field day. We have some people that are that love them. They're tricky because I built one the way that you're supposed to. And I put a good balun in it. I know it was a Granella balun, and we still had RF in the shack. I had audio interference from the CW station getting into my CQ loop on my audio link between my computer and my K3. I tried grounding the computer to the K3. It didn't help. Put ferrite on the audio wire between the K3, and it didn't help. You know, of course, that the K3 has transformer inputs, so there's no need for me to put transformers on the outside. Cars were running on generators. We're not connected to the building ground system at all. So I said, what if I just took the antenna patch panel that we had and put it on the third wire of an unused AC plug, and that solved the problem. So the trick is, if you ever use an end-fed half wave, make sure it's grounded to your house ground, and the problem goes away. And this is a Yagi, and you're probably thinking to yourself, wait a minute, I thought this was wire antennas. It is a wire antenna. I did this to operate VHF contests at W2SZ, and I wanted an antenna with very high front-to-back ratio. And if you look at all of the various antennas that you might buy, all of them are designed for maximum gain. None of them are designed for high front-to-back ratio. So I said, okay, I've got to roll my own here. So I said, okay, how am I going to do this? Well, I started out with some aluminum. I found out that it was heavy and expensive. And I needed to build a number of these to do what I wanted to do, because my plan was to have two stations 800 feet apart where I could operate sideband and FT8 simultaneously. So this particular antenna created some interesting dilemmas for EZNEC, because now you're not dealing with bare wire, you're dealing with wire which is a combination of fiberglass and nylon and PVC insulation over the wire. So you can't predict what the length of the wire is, you can't predict what the dielectric constant of the combination is. And when you start stacking these antennas, two other things happen that really makes you chase your tail. So I had fun doing this because I designed it, I built it, I measured the front-to-back ratio. And from the front-to-back ratio, which was calculated, and the front-to-back ratio that I actually got, I could say, okay, there's a problem here. How do I solve what this problem is? Well, I had to go back and actually calculate what the dielectric constant was by putting in different numbers for the dielectric constant until the front-to-back ratio of the predicted antenna was exactly what I had measured. Once I knew that the combination dielectric factor was 3.45, then I could continue my design with the antenna. Then I said, okay, what happens if I stack it? Well, two things happened. The front-to-back ratio goes to hell, and the maximum front-to-back ratio moves down about 700 kilohertz, down to 49 and a half, roughly. So now I have to redesign the antenna with shorter wires. I recut it again. And I've got to figure out how far apart to stack it. Well, experimentally, I tried different stacking distances, and the front-to-back ratio became correct when it was stacked exactly a half a wavelength apart. It happens to be 118 inches. And this is what the pattern looks like. I have a 40 dB front-to-back ratio off the entire back of the antenna. And there are notches in 2 places that are down to 55 dB front to back ratio. And if you're looking to try to do 2 things simultaneously within 800 feet apart, you could actually get lucky enough to turn them in such a way that the notch of one could be in the notch of another. I don't know how effective that is. I haven't tried it. I haven't needed to. The math of this says, okay, don't use the front to back ratio, use rear to isotropic. Well, the rear to isotropic of this is about 25 dB. So if you put 2 of these 800 feet apart, the path loss is more than 50 dB. You get 25 dB rejection front to isotropic, or rear to isotropic on one, another 20. That's over 100 dB of isolation. And now you can operate FT8 and sideband almost simultaneously. And I hope that I've inspired you with some tricks. Learn what I have done with EZNEC and tricks of using EZNEC to derive things that perhaps nobody else has tried before. And I can say is I hope this has been helpful to you in understanding how I use EZNEC. Thank you very much.